All right. So applications of logs. One of the applications of logarithms is pH. Like it's getting to be, and it's snowing outside today, so I was going to use the example about open up swimming pools and stuff. It's getting to be springtime of the year. Won't be very long. It'll be warm enough, and folks will be opening up swimming pools, and you've got to check the pH of the water and know how to add chemicals and stuff like that through testing that water. A lot of folks have to carry that. They'll get a sample of the water and they'll take it to one of the pool uh, companies around and have them test it. You can test that water at home if you know how to do the math for it. Okay, because they've got a little scale that tells them the pH. You can do the little litmus strips and test it on your own if you want to. A lot of people would rather have a professional do it. That's okay. Now here's the equation we're going to play with today. pH equals -1 times the log of, and now I'll put a bracket here, H3O plus. What that is, this right here is the concentration of the H3O plus ion. Okay. H3O is called hydronium. That's what. But in our problems, instead of writing H3O over and over, if that's the thing we don't know, we're going to put X in its place. Okay. So let's start with just a simple example here where we're taking a problem, and I'm going to thicken up my marker here so I won't have to squint so much to see it. So let's say they ask us to find the pH when the concentration of the hydronium ion is 2.5 times 10 to the negative fourth. Okay. So we're using that formula, -1 times the log of H3O plus. So we know on this problem that the concentration of that is going to be 2.5 times 10 to the negative 4. So we're going to plug that number in. So we have -1 times the log of 2.5 times 10 to the negative 4 power. And then we're going to multiply that log, whatever we get for that logarithm is going to give us the pH out of that. Okay? So go to our calculator. -1 times, and then the log button. So Skylar, this is what you asked about where the log button was. We're going to use it in this section a lot. So we're going to use that log base 10 because that's the kind of log was in the equation. So log base 10. And then our number was 2.5 times 10 raised to the negative 4. Whoops, I didn't get my caret symbol. That's the one I want. And then -4 there. Okay. 2.5 times 10 to the negative 4. I'm just going to hit enter and get the decimal approximation for that. We're going to go 2 decimal places. So 3.60 if we round that to 2 decimal places. So the pH is about 3.60. Okay? So finding that pH value out of that. That's what we're doing to start off with. That's not always what we're going to do, but it's what we did for this first problem. I'm going to look up the pH scale because I can't remember it. It's been a while since I had science and we had to do pHs. There it is. The pH scale, the more basic you are, like it's a higher number, up to 14. The more acidic you are, that gets closer to 1. A 1 pH is like gastric acid, like the acid in your stomach. A 0 pH is like battery acid. That's how strong that is. The pH here, a 3.6, that's too acidic. You want your water to be neutral. You want it to be around a 7. That's definitely not at a 7. We would need to add some different chemicals to our water to get it to be more of a, we want it, it's too acidic. We need to be more base on that. So we would need to add some stuff to that. All right. Now, let's take a different scenario. Okay. So on that one, they gave us the ion amount. Let's take a different scenario and let's say if the pH is 7.1, find the concentration of the H3O plus ion. So in this case, we have 7.10. My 1 and my 0 kind of ran together there. Equals -1 times the log. And instead of writing H3O plus, I'm just going to put an X there. Okay. Now, to solve this equation, the first thing that you need to do is isolate the log. So what do I need to get rid of on that side that's got the logarithm? What's not part of that logarithm? The -1. I'm going to get rid of that -1 by dividing by -1. That's going to give me -7.10 equals log of x. Then I've got to remember, what is the base of that logarithm when there's nothing written there? 10. So now here's where what we did in lab comes back in. So we want to take that logarithm and we're going to rewrite it as a exponential. So the base is 10. My exponent is -7.10. It's equal to x. So I rewrote that logarithm as an exponential. That got me x by itself. So that's going to tell me that right there, 10 to the -7.10, is my concentration of the hydronium ion. I'm going to work out what that number is. So this is where I'm going to go to my calculator, and I'm going to type in 10 raised to the -7.10. Hit enter. And this is where we got to learn to read our calculator a little bit. That notation right there, that E -8, is the same thing as scientific notation. Okay? It is the same as scientific notation. 7.94 times 10 to the -8. That's how you would write that. So that E, it takes the place of the times 10 to the negative whatever's after that, times 10 to the power that's after that. Okay. All right. Now, that's the concentration of the ion. So we've had one where we found the pH. We've had one where we found the ion level. Let's do another one where we find the pH, or we find the ion level, because that's the harder ones, right? So let's say we had, if the pH equals 2.7, find the concentration of the hydronium ion. These are the harder ones, right? That's the ones we want to do. So we're setting up our equation. We got the 2.7 equals -1 times the log, and I'm just going to put an X there because that's what I'm looking for. So what do I do with that? Divide by the -1. That's negative 2.7 equals log. I'm going to go ahead and write that base 10 there because that's going to help me do that. Trying to find the equation that I'm looking for. All right. Now, how do I undo that? I rewrite it as an exponential. So the base of my exponential is going to be what? 10 to the power of negative 2.7 is equal to X, or my hydronium ion stuff, okay? Now, I'm going to find out what that is. 10 to the negative 2.7. 10 raised to the negative 2.7. All right, I got a decimal here, 0.001995. Okay. I'm going to write a little bit more of that, 9952623. Now, a lot of times in this section, they will write their answers in scientific notation. Okay, so how do we put this in scientific notation? So we got the decimal place right there between those zeros. When I write it in scientific notation, there needs to be one number that's not a zero in front of the decimal. So I got to move it over 1, 2, 3 times. All right. So that's going to be 1 point. And if I round that to 2 decimal places, this 5 is going to make that become a 10, which is going to make that become a 10, which makes that become a 2. So this is really going to be 2.00 times 10 to the negative 3. It's got a negative exponent because it's a smaller number than what I ended up with. It's not a smaller number. It's a larger number than what I ended up. The number I started with was smaller. Oh, yes, ma'am. How many times did I have to move the decimal? That's where that comes from. How many times I have to move the decimal, that's going to be my exponent. If I'm moving it to the right, it's going to be negative. If I move it to the left, it'll be positive. Okay? When I'm going from standard into scientific, which is how you're going to have to do that on this stuff. Okay. All right. Let's look at an example that uses logarithms in earthquakes. That's another place that logarithms are used. The scale on the magnitude of earthquakes, the Richter scale, uses logarithms. So the magnitude of an earthquake has an A in it, earthquake, is modeled, by M equals log of I over I sub 0, where I equals the intensity and I sub 0 is the reference intensity. So a reference intensity is going to depend on where you're at in the world, okay? So reference intensity for somewhere like West Tennessee, we're going to get a reference based on the New Madrid fault, right? Because that's the one we're closest to. If you're in California, San Andreas fault is what you're closest to. So you're going to get a different reference intensity there, okay? The intensity is the measurement on the seismograph. the little, you've seen the movies and things where they'll have that little needle that's going on there. It's all digital and stuff now, but they'll have that needle on the paper and it's going crazy when there's an earthquake going on. Okay. So what you can do there is you can create a problem with that and find the magnitude of an earthquake. So let's do example D. How much more intense is an earthquake? Well, I won't spell earthquake with a Q. With a magnitude of 4.5 than an earthquake with a magnitude of 3.0. So on the Richter scale, 4.5 is our magnitude. That's not a very strong earthquake. It's got to be up there in you would feel it, but it probably wouldn't do much damage. It would do some, but not much. It wouldn't cause the building to cave in or anything like that. Might crack some walls or shake some stuff off the walls. Not super strong. 3, not as strong as the 4.5, but how much more intense is it? So the intensity is how much shaking is there. The magnitude is going to be based on what fault you're at, the intensity. If these are both in the same spot, does the reference magnitude or reference intensity even matter? If they're measured at the same spot? No, it doesn't matter what it is. Okay. So what we're going to do is we're going to set up the logarithm equation. The magnitude is equal to the log of the intensity over, and I'm going to instead of putting a number there that's hard to deal with, because we're measuring in the same spot, I'm just going to make my reference intensity a 1. Okay. And I'm going to take that equation, I'm going to set it up. I'm going to find out what's the intensity when the magnitude is 4.5. If I divide I by 1, what do I get? I get I. So now we've got an equation that has 4.5 is equal to the log of I. What kind of log is that? When there's nothing written there, it's a log base 10. So this is very much almost the exact same thing as the pH. We're going to find that by taking, okay, well that's 4.5 to the 10th power, or back up, 10 to the 4.5 power is equal to I. That's rewriting that as a exponential from a logarithm. Okay? That's a number. Okay? I don't want to round that number, so I'm going to wait until I can put both of these numbers in the calculator. Then I'm going to go over here, I'm going to do the 3.0 equals the log base 10 of I. What is that one going to be in exponential form? Ten to the third power is equal to I. Okay. Now it said how much more intense is the 4.5 than the 3.0. So I'm going to take those and divide them. 10 to the 4.5 over 10 to the 3.0. And this is where I would get my calculator out and get that answer in a decimal form. So 10 raised to the 4.5. Whoops, didn't get my raised to button. 10 raised to the 4.5 divided, whoops, get out of the dadgum exponent, then divided by 10 raised to the 3.0. 31.62 times as intense. or 10 to the 1.5 power. Same number. 31.62% or times as in tenths. So they swap back and forth every year on which one's going to be on the final. They usually put a pH problem or an earthquake problem on there. They swap every year about which one to do. On college, in Math 140, they usually do the earthquake problem. The last few years, they've had the pH problems on the Math 110 final. So that's why I do more of those. If they change and go to the earthquake, I will put maybe something on the board for us during the final to help you with that part, because that's a weird thing with the earthquake problem, but we'll get there. Okay. So some applications of finding logarithms, solving logarithmic equations there with the pH and the earthquake stuff. So pretty cool thing that they're connected to earthquakes. Yeah. Sure, I can. Yeah, no problem. Sure. Example A. That's fine. Right there. That one? Okay. All right, so the next section, I'm go ahead and get you another piece of paper, and we're going to be in section 4.5, and we get to solve equations, which is my favorite thing to do in algebra classes, is solve equations. So we're going to solve a bunch of equations in this section. So this will be the heaviest section as far as number of examples, just because we need to see a bunch of different kinds of equations along the way. So we're going to start out with exponential equations, and then we'll get into logarithmic equations. So we'll start with those. So section 4.5. You good now? Okay, all right. I was just going to ask here. All right. So section 4.5. Solving exponential and log equations. We did some of this last week. We did problems like this last week where it just said solve, and you had something like 8 to the x power is equal to 32. And we changed that 8 to a 2 cubed, and that 32 to a 2 to the 5th power. And that gave us 3x equals 5. We dropped the bases off. Remember doing that last week? Okay, so we did problems like that. And then we solved that. We would divide by the 3, and x is going to be 5/3. We found an answer. That's the kind of problems we did last week. The kind we're going to do this week are ones where you can't change the base to work. Okay, so they're going to be like this. So example B, I'm going to start out with something very similar. I'm going to have 8 to the x, but instead of a number that can be rewritten, I'm going to put a 21 over there. Because 21 is not 2 to a power. It doesn't work that way. Okay, it's 3 times 7. It isn't even an exponential number. It's just 21. Okay. Now on this problem, the difficult part is deciding how to solve that. So there's multiple ways to do this. The way that I would do this is I would look at that exponential and say, what's the base of that exponential? It's an 8. So could I rewrite this as a logarithm? Yeah, the same way we did in labs. If I rewrite this as a logarithm, it's going to be log base 8. And then what goes inside and what's it equal to? 21 goes inside. It's equal to the exponent, which is x. So I have log base 8 of 21 is my solution. Log base 8 of 21. And then I can get the decimal approximation for that. So I've got the exact answer, And then I've got the decimal approximation for that. So I'm going to put that into my calculator. So to get the log base, we're going to hit alpha window. Option 5 is log base. Hit enter. It's going to give you boxes to fill in. All I got to do is fill in the boxes. 8 of 21. Then I'm going to go, typically in this section, it rounds to 4 decimal places for whatever reason. They just decide 4 is the right number. So we're going to go 4 decimal places there. So that's going to be 1.4641 as the decimal approximation for that. And I know sometimes you get some help on like BrainFuse, or you got a tutor or somebody's helping you and they may work it differently. And I want to show you a different way to work that also works. It's the exact same number of steps, or close to the same number of steps. You could also do that with common logs. And then especially the one we're going to use is LN. If you look in the textbook for this, this is how the author of the textbook does these. I don't care which way you do it. Both ways work. So I'm going to do this one with that. So I'm going to take the natural log of both sides. So I've got natural log of 8 to the x equals natural log of 21. My log property lets me drop this x to the front. And now all I've got to do to solve that is take the natural log of 8 and divide by it. Natural log of 21 divided by natural log of 8. That is the same thing. Those are equivalent to one another. As a decimal, if I go to my calculator and I type in natural log of 21 divided by natural log of 8, make sure you close those parentheses after the 21. I get the exact same decimal answer. Okay. So if you are getting some help from YouTube or something, you may see people solving it this way. It works. It's absolutely fine to do it that way. It's absolutely fine to do the log base 8. Both ways get you the same decimal answer. The logarithms look a little different. Log base 8 of 21 looks different than natural log of 21 divided by natural log of 8, but they are equivalent pieces. Okay, so maybe a paralysis by analysis type thing. But it is one of those things where there's more than one way to get to Jackson. So we're going to try to look at that as we go along here. So let's go to example C. Let's get a new one here. Let's say we had 11 to the x power is equal to 32. And I'm going to do it with the natural log here on this one, just because I can. And there's some reason behind that. There's a little method to the madness, because if that exponent has some extra stuff happening, it's actually easier if you have the natural log in there. It kind of makes things a little bit cleaner. Okay, so I'm going to do this one with the natural log, because I know I can't make 32 11 to a power. So I'm going to take the natural log of 11 to the x and the natural log of 32. That x is going to go down to the front. And then I'm just going to divide by that natural log of 11. That's going to be my exact solution. And part of the reason I'm doing this is because where we're going to the next problem. Another reason is this is how they tend to write them on the final exam. This is how the Canvas quizzes tend to write the answers. They are the same thing. If you did log base 11 of 32, that's the same number. Okay, same number. I'm going to get the decimal approximation for that. So on my calculator, I'm typing in natural log, that's the button beside the 4, of 32, close the parentheses, divided by a natural log of 11. Enter. 1.4453. So 4 decimal places. 1.4453. Like I said, I'm using the natural logs because that's what our author likes to use. It's also how they tend to write the answers on the final exam. So I'm trying to model what you're going to see later on. Let's do another one. Let's do one that's got a little bit more happening in the exponent. So we got 3 to the x plus 5 is equal to 13. Okay, so we got a base 3, and we've got a x plus 5 in the exponent, and then we got a 13 over there. If the exponential is by itself, you're ready to take the natural log. So the exponential here is the 3 to the x plus 5. So that's ready to take the natural log of. So I'm going to take the natural log of each side. So I'm going to save myself a little writing and just do it like that. And then I'm going to have my power rule bring out that x plus 5. Then the natural log of 3 is there, and they got the natural log of 13. Now, the next thing I would do there is I want to get x by itself. That's what I need to do to finish this. So what can I do with that natural log of 3? Remember, natural log of 3 is a number. It's a decimal number, but it's a number. So what can I do on this equation to try to work toward getting x by itself? Yeah, because that's multiplying x plus 5 times natural log of 3. So dividing by natural log of 3 would get rid of it over there. That's a good step. And that's going to leave me x plus 5 equals natural log of 13 divided by natural log of 3. Remember, that's just some decimal number. We don't know what it is yet. Now we are one step closer to getting x by itself. What do I do now? Subtract 5. X equals that fraction, natural log of 13, divided by natural log of 3, minus 5. That is my exact solution. I want to get a decimal approximation for that. So we're getting the exact solution and the decimal approximation here for that. So I'm going to, on my calculator, I'm going to go do natural log of 13. Close the parentheses, divided by natural log of 3. That's the right numbers. And then minus 5. Should get a negative number here. Yeah. Negative 2 point. Going 4 decimal places, what do I round that to? 6653. The 8 that's after the 2 makes it go up to a 3. So negative 2.6653. Okay. Not too bad. That's doable. Let's go to example E. Let's say we've got e to the 3x is equal to 42. The base is the letter E. I'm not changing how I worked it. I'm still going to use natural log. But it's going to even work better on this one because remember, what's the base of the natural log? E. So if I take the natural log of each side, on the left-hand side, that natural log and that E cancel each other out. It just leaves you the 3x. That's right, Cal. So we have 3x. Scroll up so for sure see. I've got 3 times x is equal to the natural log of 42. Remember, natural log of 42 is just a number. It's a weird number, but it's a number. And then how do I get x by itself? One step. Divide by 3. So my exact answer is natural log of 42 divided by 3. My decimal approximation, I got to go to the calculator to get. Go in 4 decimal places again. Natural log 42, close the parentheses, divided by 3. $1.2459. 1.2459. Not too difficult so far. Now, let's step it up just a little bit and get one that has a little bit more going on. Okay? I'm going to go right there beside it. I'm going to do example F. And let's say we had something like this. 5 to the 2x equals 8 to the x. Okay? All right, so first thing I'm going to do is the natural logs. This is where the natural logs really come into play because on this problem, you've got 2 different bases and exponents on each side. So these, you are almost locked in to you have to use the natural logs to solve those, okay? So I'm going to use natural log 5 to the 2x, natural log of 8 to the x. Then I'm going to use my power rule, okay? Power rule says that 2x comes down to the front, and it leaves you natural log of 5. Power rule over here says that x comes down to the front, leaves you natural log of 8. Now, this one's a little tricky because you've got a part that has a natural log of 5 on it and a part that's got a natural log of 8 on it. So they are not like terms. So you can't just move them over to the other side by subtraction and join them together because they're different natural logs, different numbers there. They both have x, though. So how could I move that x over? What's going on between the natural log and the x? They're multiplying, so the move would be dividing by it. Now, this one's weird. I'm going to warn you, it's weird. What happens when you divide by that x? It canceled out. So that doesn't really help us there. Okay? So let's back up a step. If I were to move that all to the same side by subtraction, so I'm going to subtract x natural log of 8. That would give me 2x natural log of 5 minus x natural log of 8 equals 0. Now here's the trick. Both of those have x in common. Okay? This is going to be a trick that we're going to need a lot of times. If they both have x in common, that's going to allow me to factor an x out of that. Then, instead of the x canceling out, now I've got x times a number, because 2 natural log of 5 and natural log of 8 are all decimal numbers. Okay? So how do I get x by itself on this step? If I have x times a number is equal to another number, how do I get x by itself? I divide by that number. So I'm going to divide by 2 natural log of 5 minus natural log of 8. But this one ends up being a little easier because what's 0 divided by anything? 0. So this side, the 2 natural log of 8 cancels out. I get x. On the other side, 0 divided by anything happens to be 0. So our solution for that is going to be 0. Instead of the x canceling out and us getting no solution, we get an answer there with a 0. All right. We're going to do a couple of more of these kind. These are the hard ones in my book. These are the hard ones for this section. So we're going to do a couple more of these. So I'm going to take, let's do what are we on? G. And let's say we had something like, let's do 3 to the 2x minus 5 equals 7 to the x. So didn't change it by much, but changed it by a little bit. Now, the bases are different. They're both exponentials, but the bases are different. So this is where solving by natural logs is a requirement. Okay, so I'm gonna start by taking the natural log of both sides. That's going to be my first step in doing these. Then I'm going to take my power rule and drop the exponents down. Now, here is the weird thing. Because look at the stuff in the front. There's 2 pieces there. Okay? On the last problem we only had 1 piece, so we didn't have to do any kind of distributive property or anything. So on this one, this is really natural log of 3 times both of those. So that's really 2x natural log of 3 minus 5 natural log of 3. Okay. Now, the next step is get things that are the same together. So in this case, the things that are the same are the things that have x's. So I need to move this 2x natural log of 3. It needs to go over there with that x natural log of 7 because those both have x's. Just like I did on the last problem, I moved that x thing over there. But on this one, I'm subtracting 2x natural log of 3. I can't just stick them together and like reduce that down. It's going to be that expression, x natural log of 7 minus 2x natural log of 3. The left-hand side, I got negative 5 natural log of 3. That's a number. That side over there, the negative 5 natural log of 3 is a number. Now, here's where that trick comes back. Both of the problems on that side have an x. So the trick is to factor that x out. So that's going to give me x parentheses natural log of 7 minus 2 natural log of 3. Now, this stuff in the parentheses over here, that's a number. This over here is a number. This is x times a number. So I'm going to get rid of this number by dividing by it. Marker ticker. So natural log of 7 minus 2 natural log of 3. I'm dividing by that. On the right-hand side, that cancels out. All that's left is x. On the other side, I have this weird-looking exact solution. And we're going to get the decimal approximation for that. So there's my exact answer. I want to get what that is as a decimal. And I'm going to show you the easiest way to get that as a decimal is to use the fraction button on your calculator. Okay? That way you don't have to put so many parentheses in there. Okay? So I'm putting this into my calculator as a big fraction. So on my calculator, I'm hitting alpha y equals and getting the fraction button happening. And on the top, I'm going to put -5 natural log of 3. Close those parentheses. On the bottom, I had natural log of 7, close the parentheses, minus 2 natural log of 3. That's exactly what I had written down. Right? Did I get all the signs right and everything? So I typed it in looking exactly like what I had written down. Putting it in the fraction button helps with this. Okay, alpha y equals, get the fraction button, and then hit enter. Your calculator will change it to a decimal. 21.8573. This stuff is weird because it's got all that natural log stuff in there, but it's the process of solving the equations is step by step. Let's try another one. What I did on that one, yeah. So let's do example H. Let's say we had 5 to the 4x plus 1 equals 9 to the x minus 5. So this one has 2 pieces on each side of the exponent. Okay, so you got a 4x plus 1 over here, you got an x minus 5 over there. So different bases that can't be rewritten as, I can't write 9 as 5 squared or anything like that. So this is where I've got to do the natural logs to solve this. So I've got natural log 5 to the 4x plus 1. Natural log of 9 to the x minus 5. Take the exponent, drop it down. Now here's that weird step. When you do that, the next step is to take this natural log of 5 and distribute it to both of those pieces. And take this natural log of 9 and distribute it to both of those pieces. So this is going to be 4x natural log of 5 plus 1 natural log of 5. This other side is going to be x natural log of 9 minus 5 natural log of 9. Okay. So natural log, distribute your natural logs. Now, looking at these, the things that have x's are like terms. The things that don't have x's are like terms. So I need the stuff that's highlighted in yellow on one side, the stuff that's highlighted in blue on the other side. Okay? I like my x's on the left if I got a choice about it. So I'm going to move this x natural log of 9 first. So I'm going to move it by subtraction. How would I move this 1 natural log of 5? Subtract it as well. So I'm going to subtract minus 1 natural log of 5. Cancel, cancel. The natural log of 5 is canceled on the left. The x natural log of 9 is canceled on the right. Now I'm writing out what I got left. What do I have left? I have 4x natural log of 5 minus x natural log of 9 equals negative 5 natural log of 9 minus 1 natural log of 5. I know it looks awful. Now it's time for the factor trick. So on the left-hand side, everybody's got an x. Notice I took that 1 off the front of that just because it's not needed. You can leave it there if you want to, but you don't have to. So I did the little factor trick. Both of those terms on the left-hand side had an x, so I factored the x out. Now the stuff in parentheses over here is just a number. So I'm going to divide by that number. X equals negative 5 natural log of 9 minus natural log of 5 over 4 natural log of 5 minus natural log of 9. That's my exact solution. I got x by itself. To get the decimal approximation, I'm going to use the fraction button on my calculator. That's the key to this. Getting the right decimal approximation. Using the fraction button. So alpha y equals, get me the fraction button. And then I'm putting in the top negative 5 natural log of 9 minus natural log of 5. Negative 5 natural log of 9, close the parentheses, minus natural log of 5, close the parentheses. On the bottom, I had 4 natural log of 5 minus natural log of 9, I believe. Yes, that's right. So I've typed it in exactly how I had it written for my exact solution. And then I'm just hitting enter and going 4 decimal places. So what is this one going to be at 4 decimal places? 9703, because the 8 makes the 2 go up. So negative 9.9 or negative 2.9703. is the decimal approximation to 4 places. Fun, right? One letter we on I. All right, let's do one that's an exponential. E to the 4x times e to the x minus 1 is equal to 5. Now, on the left side, you got a double exponential. What is the rule for exponents when the bases are the same? You add. So we're really going to have e to the 4x plus x minus 1, not plus 1. Can we simplify this? Yeah, it's e to the 5x minus 1. All right. Now, let's get rid of the exponential. So I'm going to take the natural log of each side. What happens with the natural log and the base e? They cancel each other out. Ooh, that's nice. I have 5x minus 1 is equal to natural log of 5. This one's a lot better. All I got to do now is get x by itself. So what's my next step? Plus 1. So 5x is equal to the natural log of 5 plus 1. And then divide by 5. X is equal to the natural log of 5 plus 1, all divided by 5. That's my exact solution. Let's get a decimal approximation for that. So I'm going to use the fraction button again. Alpha y equals. First option, I had natural log of 5 plus 1. Right, yeah. And then I had a 5 on the bottom. Hit enter. 0.521 what? 19er. 0.5219er. That one's a lot easier because your base canceled out. That's really when they get easy. If the base is an E, that really works well. So every one of them up through example I has been an exponential problem to start out with. Okay, and we used a logarithm to solve it. The next set is a logarithm to start with, and we're going to use an exponential to solve it. Okay, so let's get into that. Let's say let's J. Here we have 4 natural log of x equals 36. So on this problem, we have a logarithm in there where the x is tied inside of the logarithm. The first thing that I want to do is isolate the logarithm. So dividing by 4 would really be a good idea. So that's going to be natural log of x. What's 36 divided by 4? 9. All right. Here's where the base of the logarithm comes in. What is the base of the natural log? E. So we are going to exponentiate with a base E. So what that means is I'm going to make E the base and make each side an exponent. On the left-hand side, just like natural log canceled an E with an exponent of natural log cancels each other out too. So that's just going to leave me x. On the right side, I've just got that e to the 9th power. Whatever the base of the logarithm is, that's the exponential you're going to use. Now I'm going to get a decimal approximation for e to the 9th. So on your calculator, to get the e, you hit second and then natural log. Blue button and then the natural log button will get you the E, the irrational number E. We're raising it to the 9th power. Hit enter. 8103.0839er. 8103.0839. Going 4 decimal places because that's what they do in this chapter. Okay. That wasn't too bad. That was a lot easier than the hard ones that we did. Let's do one. Let's say it started out like this. Log base 3 of x plus 6 is equal to 5. Is the logarithm isolated? Yeah. The x plus 6 is inside of that logarithm, but there's nothing else on that side that's outside of that logarithm. So now I'm ready to exponentiate. So I'm going to exponentiate with the base of the logarithm. What's the base? 3. So I'm going to exponentiate with a base 3. What happens to the log base 3 and the base 3? They cancel each other out. That leaves me x plus 6 is equal to 3 to the 5th power. What's 3 to the 5th power? It's a number, isn't it? What number? 243. So I've got a nice easy equation now to solve. I got x plus 6 is equal to 243. How do I get x by itself? Minus 6. X is equal to 237. That's nice. That's not too bad. Exponentiate to get rid of the logarithm with the base of that logarithm. You can still see that a little bit. Log base 2 of x plus 4 squared equals 24. So here's where we're going to start adding in some of our logarithm properties here. Or we can on this one anyway. What log property does the left side show that I could use? Power rule. Got an exponent there. It is a lot easier to get rid of a 2 that is a multiplier in the front than it is to get rid of a 2 that's an exponent. Right? It's a lot easier to divide by 2 than it is to take a square root on numbers, right? Square roots, not every number has a nice square root, but if I divide a number by 2, it's either going to be going into it evenly or it's going to be a 0.5 decimal, okay? So I've got 2 log base 2 of x plus 4 is now equal to 24. So that's using the power rule for logarithms. Then I divide by this 2 to get rid of it. It's going to be a 12. Now I'm going to get I'm going to get rid of the logarithm by exponentiating with a base of what? 2. What happens to the base 2 and the logarithm on the left-hand side? They cancel each other out. So I have x plus 4 is equal to 2 to the 12th power. They know what 2 to the 12th power is? 4096. Four gigabytes is what that is. If you're keeping score. Divide or subtract 4. 4092. Not too bad there. That's pretty good. say we had log 3x minus 5 is equal to log 2x plus 7. So a weird looking one here that has logarithms on both sides. It's important that they're the same base. What base are they? 10. Is there anything on the outside of either of the logarithms? No, they've got the 3x minus 5 in the inside on the left side and the 2x plus 7 on the inside on the right side. Because they're the same logarithm and there's nothing else going on the outside, I can go ahead and exponentiate with a base of what? 10. And that's going to cancel out my logarithms and leave me a good old Algebra 1 problem to solve. 3x minus 5 is equal to 2x plus 7. What do I do to solve that? Subtract 2x, good. And add 5. I heard somebody say that. And that's going to be x equals what? 12. Hey, we got our answer. We didn't, and we don't even have to get a decimal approximation for that one. That worked out real nice. Got to be 12. Okay. So if it's a single log on each side, exponentiate, get rid of it. It really just drops the logs away. Where it gets a little more interesting, y'all hate when I say that. It's what it's doing, is on one like this. So this is example N. Let's say we had log of 2x plus 1 equals, or not equals, sorry, let's do a plus sign in between there. Plus log of x equals log of x plus 8. No, can't do that right away. Because the left side has 2 logarithms on it. This is where the log properties, where I've got to use those to help me. So how do I turn the left side into a single logarithm? What property does addition turn into? Multiplication. So this is really log of x times 2x plus 1. I'm writing an extra step here. That 8 didn't end up looking good there. So that's going to be log of x squared, 2x squared plus x is equal to log of x plus 8. Now that's a little bit more like what we just did on example M. Because now I have a log on each side, one single log on each side. So I can exponentiate with the base 10 and cancel out those logs. Now I've got a problem that's got 2x squared plus x is equal to x plus 8. This is a little harder problem to solve because it's got the x squared and the plain x in it. So what do I need to do? Subtract x to get what together? All the plain x's are the like terms, right? So I've got 2x squared is equal to 8. What can I do now? Divide by 2. I like it. That'll work. That's going to give me x squared is equal to 4. Okay, if I take the square root into this problem, what else do I have to remember? This is back from plus or minus. Anytime I bring the square root into the problem, we got to put that plus or minus in there. If we don't, we're missing half of our answers. So what is the square root of 4? 2. So I have 2 answers. I have x equals positive 2, I have x equals -2. I need to check these. Check to make sure there are positives in the logs of the original equation. So in the original equation, I had log of 2x plus 1, and I had a log of x, and then I had a log of x plus 8. I'm going to check the positive 2. Positive 2 times 2 is 4. 4 plus 1 is 4. That works. Positive 2 in there is a positive 2. That works. 2 plus 8, positive 10. That works. The positive 2 is a good answer. It checked. The -2, if I plug that in here, 2 times -2 is how much? -4 plus 1 is -3. You cannot have negatives or zeros inside of logs. It's only positive numbers. Because that ended up being a negative inside of there, that's what we call an extraneous solution. That -2 is extraneous. And we found it, but it doesn't work. Sometimes they will all work. Sometimes one of them gets thrown out. It's very unlikely, but there are occasions where both of them get thrown out. It's not very often, but it could happen. All right. Let's do one more. Donut example. Let's do log base 3 of 4x minus 1 minus log base 3 of x plus 1 equals -3. All right. So now this one, we've got 2 logs on one side. That makes it difficult to solve. So can we condense that into a single log? How? Division. Subtraction becomes division. That's the log property that we're using that we learned last week. So this is going to be rewritten as log base 3 of 4x minus 1 over x plus 1. It's going to still be equal to -3. So we have condensed that by the quotient rule of logarithms. Subtraction turns into division. Addition turned into multiplication earlier. Here, subtraction turns into division. Now I'm going to get rid of that logarithm. So I have a base 3. So I'm going to exponentiate with what? 3. On the left-hand side, the log and the base 3 go away. That's good news. So I've got 4x plus 1 over, that ain't right, is it? Minus 1, yeah, the plus 1's on the bottom. 4x minus 1 and x plus 1's on the bottom. On the other side, what is 3 to the -3 power? 3 raised to the -3. I'm going to hit math, enter, because I'm pretty sure it's a fraction. It's 1 over 27. Instead of the decimal, I wanted the fraction because I don't want that decimal because it was repeating, and that messes me up if it's that repeating decimal. I need it to be a fraction. So it's 1 over 27. Now, here's where we got to remember how to solve fraction problems. How do you solve a fraction equal to a fraction? Say again. Do I straight across or Yeah, diagonally. Bottom times top. So I'm multiplying this times 1 and then 27 times the 4x minus 1. So I got 27 times 4x minus 1 equals 1 times x plus 1. I want to distribute those. 27 times 4 would be 80 plus 28 is 108x minus 27. And that's just x plus 1. Now, how do we solve that one? Subtract x and then add the 27 over. So I'm going to change colors there. Subtract x, add the 27. So it'd be 107x equals 28. And then last step, divide by the 107. X is equal to 28 over 107. 28 is divisible by 4 and 7. 110 is not divisible by 7. It is not divisible by 4. So that means that doesn't reduce. If I'm not sure, 28 divided by 107, math, enter. It'll reduce it for you, if it will. If that one doesn't. Now, still got to check that because it was a logarithm problem. But if I go back to the original, 4 times a positive fraction there, 4 times 28 divided by 107, 4 times 28 divided by 107 minus 1. It's a decimal, but it's still positive, so that part's okay. And then the other logarithm in there was x plus 1. If I add 1 to something that's already positive, it's going to be positive too. So that works. That one checks as okay for both of those. So 4.5 is the hard section of tonight's stuff. It's the tough section to do. Okay, so we're through it. Let's go to an easier section that definitely doesn't have as much heavy lifting in it. It's financial math. So this is one of those lessons that I get frustrated every time I get on social media and somebody says, they never taught us anything about money in school. Yeah, we did. Because this is stuff I teach in high school math. It's compound interest. Okay. So compound interest. So this is financial math, 4.6. Financial math. We did a little bit of this last week. But today we can solve equations and find out how much time we need or different variables. Last week we kind of just plugged in and worked out. Here we're going to actually find out what lengths of time. So compound interest, it has that formula, A equals P times 1 plus R over N to the NT power, where A is your account value, P is your principal investment. You might call it the deposit. That's what it is. The R is your interest rate. And I'm going to write decimal because you'll get an interest rate as a percent. We need to put it in as a decimal into the formula. And then N is the number of times compounded per year. Remember we talked about that a little bit last week. Quarterly would be 4 times a year. Semi-annually would be twice a year. Monthly would be 12 times a year, that sort of thing. Okay, that's what that N is. T is time in years. So that's our first formula that we're going to use, okay? So let's take an example here. How long should I leave an investment of $2,000 in an account with 7.5% 7.5% interest compounded quarterly to double my money. Okay. So, again, we're going to use that formula. Account worth equals principal times 1 plus R over N to the NT. What is my principal investment? $2,000. That goes there. If I'm doubling my money, what's my account going to be worth? 4,000. So that goes there. What's my interest rate? 7.5%. What is that as a decimal? Move it to the left twice. 1, 2. 0.075. Compounded quarterly. What's N? 4. I don't know the time. That's what I'm looking for. So that's a 4T power. Okay. So I have this equation set up where T is my variable. It's the variable in the exponent. So this is one of those exponential equations. We're going to solve it using logarithms. So I got to isolate the exponential. So the first thing I'm going to do is get rid of the 2,000 by division. That's 2 equals 1 plus 0.075 divided by 4 to the 4t. I'm not going to really work out that number. I'm going to let the calculator do it in a minute. So I'm just leaving it there. Now, how can I get rid of the exponential when the bases are weird like that? Well, this is how we did the problems in 4-5 at the beginning there. We're going to take the natural log of each side. And that's going to allow me to drop the 4t down to the front and have natural log of 2 equals 4t times the natural log of 1 plus 0.075 divided by 4. So using the natural log, I was able to use my power property and pull the 4t down to the front. Now, what's going on between the 4, the t, and the natural log? They're all multiplying together. So to get rid of that and leave me the t, all I'm going to do is divide by 4 and the natural log of that number. That's going to cancel the 4. It's going to cancel the natural log. The only thing left is t. That's the time. So the natural log of 2 divided by 4, natural log of 1 plus 0.075 divided by 4. I want to get that as a decimal because that doesn't mean much to me about how many years. I'm going to figure out what that is as a decimal. So natural log of 2. I'm going to use the fraction button on my calculator because that's going to help me. Natural log of 2. On the bottom, I got 4 natural log of 1 plus 0.075 divided by 4. Close the parentheses. And hit enter. 9 let's go 4 decimal places like we've been doing. So 9.3283. Years. It's going to take my money 9 years, and 0.3 of a year would probably be close to 4 months. A third of a year is 4 months. So 9 years and 4 months to double my money. If I just put $2,000 in it and left it. Okay, that's how long it takes me to double my money at 7.5% interest. Y'all find me an account that gets 7.5% interest. We'll go put some money in it. Okay, there ain't none. They don't give that kind of money away. Not unless you're going to leave it there for a long, long time. All right, now that's compound interest for compounded a certain number of times a year. Another type of problem that you come in contact here with is what's called continuous interest. It has, I call this the PERT formula because it spells the word PERT. They used to make shampoo called PERT. It came in a green bottle. I don't know if they still make it or not. But it, PERT, P times E to the RT. P is still your principal. R is still your interest rate. It hadn't changed any. T is still time in years. A is still account value. That's all the same. The difference is with continuous interest, your interest, whatever interest your account earns, it's continuously dropped back into the deposit. On the other example A, it was only dropped in every 3 months. They save up your interest, and then at the end of the 3 months, they put it back in. Here, they put it in instantaneously. Every time it earns anything, it goes back in. So it gains it more often. It should be a little bit faster. Okay, so let's try to work this a problem here. Example B. How long does it take to turn $1,200 invested at 6.75% continuous interest into a value of $5,000. So in the problems, you're going to see these words: continuous interest or interest compounded continually. The word continuous will be in the problem. Okay, so you're going to see that word, and that's going to tell you, hey, that means use the PERT formula. Okay, so A equals PE to the RT. That's how I know to do that problem with that formula, because it said continuous interest. If it said compounded monthly or compounded quarterly, that's how I know to use the other formula. So knowing which formula to use is key. All right. So account values the $5,000. Principal investment is the 1,200. E is the base. R is the decimal for 6.75, so 0.0675. Move it 2 decimal places. 0.675 times T. So T is my variable. Again, I'm trying to find time. How long does it take me to get to $5,000 on this account? So that I know if I need to put some more money in there, if I can't wait. Okay. So what's our first step in solving this problem? Divide by 1,200. So we're more than doubling our money here. We're quadrupling our money and then some. So that's going to be 52 over 12. 52 divided by 12. I'm going to write that as a fraction, 13 over 3. The reason I'm not making it a decimal there because it was a repeating decimal. If it was a terminating decimal, like something like 4.5, I just write 4.5. But because it was a repeating decimal, so when I put that in the calculator, 5,200 divided, or not 5,200. Why did I do 52? It's supposed to be 50 divided by that. I did 5,200. Let's do 50 divided by 12. 5,000 divided by 1,200. That's a better number. Still a repeating decimal. So I don't want to round that. I want to use the fraction for that. I don't want to round until the very end. So I'm going to write that as 25 over 6. Sorry about that. And then I have e to the 0.0675 t. So I have a base e there. How do you get rid of base e? Natural log. Okay? We're trying to, any of the exponential problems where the variable's in the exponent, we're going to use natural log anyway. So I'm going to take the natural log of both sides. On the right-hand side, that natural log and the e cancel each other out. That's the beautiful part about this one. And I get 0.0675 t is equal to whatever the natural log of 25 over 6 is. I'm going to leave it like that because I know it's not a pretty number, because 25 over 6 is not a pretty number. If I take the natural log of it, it ain't going to get prettier. Okay? Last step, divide by your 0.0675. So my time is whatever the natural log of 25 over 6 divided by 0.0675. I'm going to get that as a decimal now. I want to round this at the end, okay, because I'm getting my final answer here. Going 4 decimal places like we've been doing. So natural log 25 divided by 6. We'll get that answer and then divide it by 0.0675. If you wanted to do the fraction button, that's probably a little safer. Natural log of 25 divided by 6. Close the parentheses. Go down to the bottom. Put your 0.0675. 21.1425. That's a little long. I don't know if I could wait 21 years just to get a few thousand, a couple, was it about $4,000 that I was getting? That's an awful long time to wait on $4,000. What's the inflation rate now? Do y'all know? At one point in the last 10 years with COVID and all that, the inflation rate had got up to 8%. So if you had an investment somewhere and you weren't getting 8% on it, you were actually losing money by leaving it there. Now it's gotten back down. I want to think the inflation rate is getting down closer to like 5, 4.5, 5. So if you can gain, how much? 2.40. That's really low. It's normally over the last 30 years has been about 3%. Yeah. Okay. So the inflation rate has gone down. it had inflated quite a bit during COVID and the years right after that because of the cost of living for that and all of the out of jobs and stuff like that. So there was a really large inflation rate. So now is the time where you can actually get ahead a little bit by investing some. When it was that way, it was pretty hard to. You had to find some accounts that were giving out like 12% or something like that, so that you could make money. Because if you're not covering the inflation rate while it's in the account, it's not making you any money. Because every year you leave it there, the inflation rate makes it worth like whatever the inflation rate. If it's 2.4% now, your $100 at the end of this year, if you didn't do anything with it, at the end of this year, it'll only buy $97.60 worth of stuff because that's how inflation works. It takes that many dollars off of 100 at the end of the year, and it's just not worth as much. That $100 is not worth as much at the end of this year. So when you see them talk about, they'll talk about somebody that was an athlete back in the 80s and they made this amount of money in their contract, and if you put that into 2026 dollars, it's a lot more money than what they were making then, because 1980 something money was the inflation rate from 1980 something up to 2026 creates a huge jump in money, because inflation for 40 something years, 3% every year, that adds up pretty quick. So every $100 added up. If you did 3%, $3 added every year. So $3 the first year, $6 the next year, $9 the next. It adds up fast out of that for every 100 that you make. All right, problems for 4.4, 1 through 97 out of the text. That's good practice. Problems for 4.5. 1 through 105. There's a lot in that. Remember, that's our tough section. And then 4.6, not as much stuff there. 1 through 51 odds, if you're looking at the textbook. Next week is spring break, no class. You do have a test when we come back. We'll have labs and an exam when we come back. So make sure you're doing the review sometime between now and when we come back on March the 30th, I believe, is the date that we come back. So y'all have a great week. Be careful going home. Don't get stuck in the snow. I think it's about done with the snow. I'm about done with the snow.